All right, so this section called parallelism preserved and protected. So it's 5.5. We're still in chapter 5 about geometry. So do you guys all know what parallel is? Everyone's okay with parallel? Yeah, think about your definition of parallel. If you don't know, that's okay. We're going to talk about it today. What does preserved mean? What does protected mean? What does that mean? Okay, so that's what we're going to start doing. So here's our very first question. Two lines are parallel. Two lines in a plane are parallel if. How would you prove that two lines are parallel? How would you prove that two lines are parallel? Okay. So yeah, exactly. Someone said they'll never cross. That's a legit way. Lines are always straight. I know it sounds so funny, but when people say straight line, that's redundant, right? Someone said they kind of go in the same way. I understand what you're saying, but there's a better mathematical, stronger way to say that. So I want to make sure. Angles are congruent is an interesting thing. I think you're thinking of something that you learned in the past, which is really good. Yeah, I'll take either of those. I'll even take a couple more. So some people say, so like two lines are parallel if they never intersect or they never cross. Yeah, someone else says they have an equal distance between each other, which is really, really good. Um, let's see. I'll just leave it right there. Okay. There's one more way that you can tell, and I think you learned this last year, and it has to do with a grid. So if I wrote a line that said y equals to 2x, and I wanted to graph a line that was exactly parallel to this, can someone give me an equation that's exactly parallel to this? Y equals what? Just guess. It's okay if you're wrong. Give me a number. 5x. Ah, man, those two aren't parallel. Shoot. Someone said negative 2x. Okay. Ah, they're not parallel. Try again. Your goal is to try to get them parallel. Okay, 3. Still not parallel. 7. Still not parallel. Ah, someone says 2x plus 2. Ooh, parallel. All right, fine. Give me another one. Y equals. Give me another one. Give me another line that's parallel to this. 2x doesn't count because look, that's the same exact line, right? Very good. Can you put that out into the public chat? Give me another one. Look at the similarities between these two. Give me another line that's parallel to it. Give me another line that's parallel to it. Yeah, someone says 2x plus 3, Miss Johnson? Yes or no? Yes, absolutely. Yes or no? Is this a good one? Did she find a good one? Everyone says yes. Everyone says no. What? Good. Use your observation skills to make me another one. Very good. Give me another one. Boom. Boom. Give me another one. Come on, y'all. Someone sees this. Someone sees the pattern. Your job is to find patterns. You make your life a lot easier when you look for patterns. Yeah, give me one. 2x plus 1? Okay, fine. 2x plus 1. Yes or no? Yeah, give me another one. Come on, y'all. Go faster. Or are these the only four? Oh, 2x plus 5. Yes or no? One said 2x plus 10. Yes or no? Ooh, someone says 2x minus 2. No. Oh, no, that's right. What's the common trend here, y'all? Yeah, 2x. So two lines are parallel if they have the same slope. Okay. This is you being a detective, right? Someone said that they were going to go watch a movie, and part of the movie is to figure out, like, right, you don't know in the movie that you're about to see, right? You don't know, let's say you're sitting in the audience, you don't know who the who the person who's doing the wrong thing is. Like, you're learning along with all the characters, right? So your job is to look for the common pattern, the common trend. This is what math does. This is another gift of math, right? Is to be observant and see. And then to like make a conjecture. You guys were all wrong in the beginning. I'm so glad you were wrong. You said 3x. I was like, imagine if I was like, no, right? I didn't do that. I was like, that's wrong. Try another one. Try another one. Try another one. Until you got to the point where you're like, I think it could be 2x plus, I don't know, minus 7. Oh man, Jonathan, I found another one, right? That's your job. Your job is to look for patterns, okay? If you look for patterns, the rest of math will be so, you know, I don't know. It'll make a lot of sense to you. So one of my favorite mathematicians, she describes math as the ability to look for and describe patterns. That's it. Everything else falls in those categories. So what you're going to be able to do today is determine when a line will be parallel to its pre-image, meaning the original dude, after a translation, rotation, or reflection. And then I want you to build a system of geometry-based definitions, postulates, and theorems. What kinds of transformation produce lines that are parallel to their pre-image? What could you do to a line? Could you translate it? Can you rotate it? Can you reflect it? And it'll still be parallel, right? That's what they're asking. How are definitions, theorems, and postulates different? And why do we need all three? Okay, so we're going to talk about those things. We're going to move forward. So we're going to do, we're not going to do the three reads, but you are going to do the three reads. So read the introductory paragraph of the task, focusing on the understanding and connections being made to prior tasks and the structure for thinking about proofs. In pairs, one student describes the details of the context, their partner is going to be filling it in. So we're going to do this together so that you guys are more comfortable, because we're still learning how to do proofs. It says, in a previous task, how do you know that? Remember, we did that. I think it was 2 sections ago. You might have wondered how you knew this figure, which was formed by rotating a triangle about the midpoint of one of its sides, was a parallelogram. Everybody see this? This is a parallelogram. Everybody okay with that? You may have found it difficult to explain how you knew that the sides of the original triangle and its rotated image were parallel to each other, except to say it just has to be so. There are always some statements we have to accept as true in order to convince ourselves that other things are true. We try to keep this list of statements as small as possible and as intuitively obvious as possible. And, oh, I put that twice. I'm sorry. I got excited. Okay. For example, in our work with transformations, we have agreed that the distance and angle measures are preserved by rigid transformations. Rigid transformations are translations, also known as moving or sliding. Reflections, which is known as flipping, and rotating, which is mathematically known as rotations. spinning or rotations. Since our experience with these transformations suggests that translating, rotating, and reflecting figures do not distort the images in any way. You know this is true, right? Let me prove it to you. Okay. Everyone pick up your phone. Look at your phone. Don't unlock your phone. Just look at your phone. Everybody good? Now move it to the right. Okay. Did everybody move it to the right? Did it change shape as you moved it to the right? It didn't? Are you sure? So when I translate something, it doesn't change shape. Okay, let me try you. Like take your hand and move it to the right and to the left and to the right and to the. Thank you for saying hi to me. You guys are so cute. Okay, so did my hand change? Did my hand change? Like, wait, look at it here. Wait, I'm moving it. I'm moving it. Did it transform into a puppy? Did it? No. So translation holds that it doesn't change it. Okay. Rotating it. So take your hand and go this way. Is it changing shapes? No. Some people call this upside down. Like if a triangle is drawn, here, I'll draw you a triangle. Some people say this, and I think it's interesting. Some people say that this is an upside down triangle. I'm like, nope, still a triangle. Do you want me to prove that this is just a triangle? When you sit down or when you lay down, or when you perhaps do a cartwheel or a handstand, do we now call you upside down John? No, we don't. We just say, dude, John's doing a handstand. Okay. So likewise, parallelism, which within a figure is preserved by rigid transformations. Meaning, if I have a parallelogram and I take him and I slide him over, can I do this? Can I slide you over? Yeah. Did he change shapes? Everyone say no. Okay, I can't rotate this one because Zoom doesn't let me rotate stuff. What about if I reflected him? If I reflected him, like, and I showed him himself, is he now not looking at a parallelogram? Is he going to be like, oh my gosh, I am a lion? Everyone say no. No. Okay, so the image is still a parallelogram. The opposite sides of the new quadrilateral are still parallel. So if I move it, if I reflect it, if I spin it, still the same. I can't do this. I need to go here. Thanks. Okay, so wait, did I finish? No, I did not. Here it is. Okay, this one says mathematicians. You are a mathematician. Okay, you're like, no, I'm not. Yes, you are. Mathematicians are humans. Are you a human? Wait, shoot. I don't know. Are you guys humans? Okay, just making sure because you guys all giggled at me. So, are you human? Yes. Do you do something called math? Yay, you're a mathematician. That's all. That's all you need to be in order to do math. Okay, we call statements that we accept as true without proof as postulates. Okay, the reason why we don't have to prove these is in order to prove certain things, we have to start with like a base knowledge of agreements, right? Like, let's just say I asked you, what's your favorite movie? The very first thing we need to agree on is what we are defining as a movie. Does that make sense? If we don't agree on that, then someone's going to be like, oranges are my favorite movie. And everyone's like, dude, orange isn't a movie. And you're like, but you didn't define a movie, so I can say anything I want. And then they'd be right. So we all have to accept the basic definition that what a movie is. It's something that's on film, right? It's something that could be, I don't know, how would you define a movie? Shoot, that's an interesting question. It should be more than an hour long. Usually it's not like episodes of, over and over again. Some people call it a film. That's right. Technically it's interesting though, because it's not, is it still carried on film? Is it like, cause they're all digitized now. So who knows? Okay. Anyways, let's move on. So we all have to agree on our very first definition of what a movie is. So same thing goes here. So those are called postulates, things that we just agree on. Okay. Statements that are supported by justification and proof are called theorems. So a theorem is something that we have proved or can prove. Does that make sense? Okay. Knowing that lines or line segments in a diagram are parallel is often a good place from which to start a chain of reasoning. Almost all descriptions of geometry include a parallel postulate among the list of statements that are accepted as true. So there's going to be a postulate that we're going to show you, and you're going to be like, oh yeah, that makes complete sense. I agree with this. In this task, we developed some parallel postulates for rigid transformations. Okay, so I'm gonna go over here. Sorry. I'm going to go over here. And here's our first one. So under what conditions are the corresponding line segments in an image and its pre-image parallel after a translation? So translation just means to pick it up and move it. Slide it up and down, left and right, diagonally, whatever you want to do. That is which word best completes the statement. After a translation, corresponding line segments in an image and its pre-image are blank parallel. So after a translation, do you think it's sometimes, always, or never? Very good. So some of you said, Miss Johnson, I don't know if it's C or B. You knew that it could not be never, right? So corresponding line segments in an image and its pre-image are parallel. So I think some of you are not understanding this part, so I'm going to draw you a picture. And I'm going to use my thing to show you what they're asking. Okay, so here. So under what conditions are these line segments? So I'm going to draw you, I don't know, some weird shape like this. Let me clear this guy off. So I'm going to take this guy and I'm going to copy him. Okay. There. I shifted, do you guys all see my translation? I shifted him over to the right and down a little bit. So after a translation, corresponding line segments, so this guy and this guy, this guy and this guy, are always, sometimes, or never. Most of you said always. It's actually sometimes. You guys are like, what? Tell me to look at two of them. Does anybody see anything? Anybody see anything? Yeah, it's sometimes. Technically, if they're shifted down directly, it's this line is not parallel to this line, right? Does everybody see how this line is not parallel to this line? Because they're on the same line. Is everybody okay with sometimes? So whenever you're doing these always, sometimes, never, the idea is to think about all of the cases. Okay? All of the cases. So because I shifted this, I mean, I can even do this one. Can you pretend that this is an actual line? Do y'all see how this is the same? That's why I was moving it around this way. And I was hoping someone would catch on, like, oh, look it, if it's along that same line, right? Okay, so let me put that there. So yeah, because it's the same line, it's technically not parallel. Because you all said that the definition of parallel means it never intersects. Do you guys remember that? Well, these two lines are intersecting, so they're not parallel, right? Okay, so we talked about this. The reason why is if they are on the same line. So now they want us to write a postulate for this. They want us to write a postulate. So a postulate could be like you making a statement that says, after we did this, this is what could happen. Okay. So I'm gonna start you off. I can't write anything. Hold on a second. So I want you to start off your postulate like this. After translating, how about after a translation? Corresponding, I'm just copying here, corresponding line segments. What did I do? Oh, I did it wrong. Corresponding line segments in an image and its pre-image. Okay. Are, what did we say? Okay, so now I'm going to change it. So are always parallel or lie along the same line. So this is a postulate. Okay. So do you guys agree that this is true? This is something that makes sense and it's true? Does everybody see this? Kind of, sort of. Okay. So let's do rotations. I can't do rotations in this thing, but I want you to ask the same thing. Under what conditions are the corresponding line segments parallel after rotation? Yes, absolutely. When would it be doable? So let me bring up something, and then so while you all are thinking about this, I'm gonna bring up Word, because Word, it does a better job of parallel stuff than. What do you guys think? Always, sometimes, never? Never. Sometimes. I got a never, I got a sometimes. Why is this taking so long? Come on, buddy. There it goes. Yeah. Okay, here we go. So I use this because it's easier for me to draw. So I'm gonna go draw. No, I want a shape. Sorry. I'll use this guy. Sure. Okay, so what I'm gonna do is I'm gonna copy this guy, and I'm gonna rotate this guy, and I want you to find out when what? When are the segments parallel after a rotation? So you tell me. Here's a rotation. When are they parallel? Tell me when to stop if you see any parallel. Here, it's parallel here. Do you guys all see it? This is parallel. This is parallel to this. But technically, this is a rotation. I mean, this is a translation, right? So a rotation would be this. So now tell me, do you see another time that these two are parallel? Do you see another time? Yes or no? In a rotation. Yeah, very good. There's another time right here, right? Do you guys all see that? So, but there's also not. So clearly this is going to be a sometimes. Yes? This is a sometimes. So when would it be parallel? Right? When would it be parallel? When would it be parallel? How many degrees is this? Anybody know what this is called when I go all the way around? Yeah, very good. When I go all the way around, that's called a 360 for those of you who watch any kind of extreme sports. For those of you who watch extreme sports, what is this called? Yeah, this is called a 180. So this is when they for sure that they'll see it. Okay. So I need you to write one that's like this. So I'm just going to copy this because I can. This helps me type faster. So is it after a translation? No. After a rotation of how much? Yeah, 180 degrees. Corresponding line segments in an imminent and its printed are always parallel or lie on the same line. That's true too. Look at that. You guys all get this? Same thing for reflection. Reflections look like this. I can only do it here. How do I do this? I forgot. Word has changed, yo. Oh, they don't have it anymore. There's a way for you to reflect it. I cannot do it. All right, can you imagine it being reflected? You guys all see my reflection? What about reflections? Always, sometimes, or never? Always, sometimes, never. So, because I'm going to just do it like this. I'm going to pretend that I reflected this guy down this way. Is that okay? Pretend that I reflected him down this way. Do you see how this is parallel to this? Yes. What about this? Is this parallel to this? Is this parallel to this? So it's not always. Again, this is sometimes. So again, I'm going to copy this statement. Right? How would you fix this? What would you say for this one? Yeah. I would just write reflection here instead. Right? Okay, let's continue. So it says, based on this reading, right? Oh, I just did that. So here are your postulates, okay? So the thing that I want you to think about whenever you guys are doing this is what pattern do you see in terms of your observation?